Today we'll be considering vector subspaces and linear independence among vectors, leading up to the idea of a direct sum. We call a non-empty subset V0 of a vector space V to be a linear subspace if it's the case that for any two vectors in V0, then their sum is in V0, and for any vector in V0 that its scalar multiple is in V0. One way of phrasing that is by saying that the subspace is closed under vector addition and scalar multiplication. Clearly, a linear subspace is itself a vector space over F since it obeys all the axioms, as long as we ensure that it contains the zero vector. To a linear subspace, you can associate some equivalence relations on the whole vector space. That is, we write that two vectors in the vector space V1 and V2 are equivalent mod the subspace V0 whenever V1 minus V2 are in V0. That is, if you consider the difference of the vectors and if it lies inside the subspace V0, then you say that those two vectors are equivalent to one another. This is an equivalence relation because it satisfies reflexivity. That is, V1 minus V1 is the zero vector, which is in the subspace. It's symmetric since if V1 minus V2 is in the subspace, then V2 minus V1, which is the negative of V1 minus V2, is also in the subspace since the subspace is closed under scalar multiplication. And it's transitive since if V1 minus V2 is in V0 and V2 minus V3 is in V0, then V1 minus V3, which is V1 minus V2 plus V2 minus V3, is in V0. The equivalence class of these vectors V and V is a subset V plus V0, which is the set of V plus W, where W is in V0, which is a subset of V. If we have a vector V1 is equivalent to V1 prime and a vector V2 is equivalent to V2 prime, then V1 plus V2 minus V1 prime plus V2 prime is equal to V1 minus V1 prime plus V2 minus V2 prime, which is in the subspace, since V1 minus V1 prime is in V0, and V2 minus V2 prime is in V0, and V0 is closed under scalar multiplication. Hence, the equivalence relation respects vector addition, and similarly we can check that it respects scalar multiplication. Thus, the algebraic operations on the vector space V extend to the set of equivalence classes, so this also has the structure of a vector space over the field F. We denote this vector space as V quotiented by V0, which is called the quotient space of V by the subspace V0, or we can write the vector space V modulo V0. For example, the subset of F to the n consisting of vectors for which the first m components are all 0 for 0 is less than m is less than n is a vector subspace V0 within Fn. And we say that two vectors in Fn are equivalent modulo V0 when precisely their first m coordinates are the same, since if you take the difference of those, we will get the first m coordinates all being 0, which is in V0. Hence, the quotient space F0 over V0 can be identified with the vector space F to the m. From here, we will note that if we have two linear subspaces of a vector space V, which will denote V1 and V2, it is clear the intersection is also a linear subspace of V. If the intersection is the trivial zero subspace, consisting of only the zero vector, then we say that the two linear subspaces are said to be linearly independent. The sum of any two subspaces is the subset V1 plus V2, which is a set of vectors such that V1 plus V2, where V1 is from V1 and V2 is from V2, is a subset of V, and it's easy to see that it's also a linear subspace of V. With that, we've led up to the idea of a direct sum by considering linearly independent subspaces, and we'll pick up with that next time. Thank you for watching.